Hello. In this session, some concepts regarding differentiability of functions on known spaces will be reviewed and discussed, and the relation to subdifferentials and maximal monotone functions and the notion of accretivity will be discussed. First, I start with the definition of the Gaussian derivative. Let A be a norm space and suppose that phi is a mapping from E to R, and it can, for the range of this function, get even infinity. But for simplicity, I write just R here, and this limit phi of x plus lambda y minus phi of x over lambda when lambda goes to 0, if exists, is the directional derivative of phi at the direction y, at this direction. And if exists, we write this like phi prime x in the direction of y, and it is indeed phi of x plus it is a different derivative of this function phi of x at the point this is a vector, and with respect to t, we have this fraction for this symbol. So it is not enough just to have a derivative in one direction for our work. And if the phi is differentiable at every direction, we say that phi is pressure. Pressure is for uniform case, and the simple case is Gaussian. Which is defined by this. We say that phi is Gaussian differentiable if and only if this limit exists and it is uniform with respect to the directions. Here the directions is y. So only on y, and y here can be taken in the SP, for example, the unit sphere, and no, it is for Fresche. I will write it. This is just for all here because we have for all points the existence of this limit. So I can say that in this case, for any y and e. But if you search in the books, you see another definition for Gaussian differentiability. Usually, this limit equals to linear functional over y. They write like this, but generally we cannot reduce this limit is equal to this linear mapping over y. But in some cases, like phi is convex and usually continuity, we have this one, and we can obtain a linear function that this linear function over y equals this limit. We calculate for the mapping norm and show that since this mapping is convex and continuous, there exists a linear mapping, and indeed in the dual of the space with this condition. Before doing this, I compute for mapping like phi of x equals the norm of x to the 2 for the space Hilbert. And it is easy to obtain this one because it plus lambda x minus phi of x over lambda. Here is the norm of x plus lambda x to the 2 minus the norm of x to the 2 over lambda. And by using the inner product for Hilbert spaces, we may write like the norm of x to the power of 2 lambda 2, the norm of. Here I need to write y and y2 minus 2 x and lambda y. It's plus minus x2, and by simply find these factors, we obtain this one by eliminating also lambda from the denominator and the numerator. We have lambda y2 plus 2 xy, the inner product of these two. And if we tend lambda to 0, we obtain this one, 2. And I write here 2 inside the inner notation. And you see that this limit is uniform for all x and y in a ball, in a circle, in a sphere indeed. And it shows that phi is Gaussian differentiable and the linear mapping that we obtain here is 2x. This phi prime of x is called the Gatu derivative of phi at point x. So if we call this derivative, we mean this equation and the existence of the limit, both. And there is another definition for pressure. If the limit is uniform, phi of x plus lambda y minus phi of x over lambda, if this one exists uniformly on y in S1, or I write here SE, then we say that the norm of the space is pressure differentiable. Say that the norm of E is pressure differentiable. And there is a definition that is connected to get to differentiability. It's interesting. We say that E is smooth if the duality mapping J, which is defined like the star in E star, such that X and X star is the norm of X to the 2 equals X star to the 2 is singleton. I mean, it has a single element. By the Banach theorems, we know that J of X is non-empty, but we don't know that it is single-valued or multi-valued. And in last session, we saw examples even in the finite dimensional space that J is multi-valued. So the smoothness doesn't have anything to do with the dimension of the space, but it has something to do with differentiability that we discuss here. We will find out that smoothness is equivalent to the get to differentiability of the norm of a norm space. And from now on, we consider this mapping, and we obtain some results for this special function, and then we obtain more general results for mappings from E to R. I remind an inequality for norm spaces we have for all x and y in E and lambda greater than 0 and x a non-zero x and y with this property, this inequality is full. Y j of x. We sometimes write the elements of j of x by this notation. And this one is less than or equal to the norm of x plus y minus this. And we have in the right side y and j of x plus lambda y over the norm of x plus the lambda y, and you see the relation that get to differentiability may have with the duality mapping here. It is easy to show. It is an elementary indeed exercise. It is just enough to add here x2 and subtracting by x2 and writing this like x and j of x and doing some elementary calculation to obtain this inequality. And by this inequality, we obtain an interesting result. This is a theorem that says the following are equivalent. First, E is smooth. That's the duality mapping J is single value. To this mapping from the unit sphere of E to the unit sphere of E star, any selection like this, J of x is norm to weak star continuous. And we have this one instead of any, we may write for some selection, and this one false, and they are equivalent to this interesting statement that the norm is Gatu differentiable, and at here I mentioned that we can have this statements for right for any point, because sometimes we eliminate the region, the 0 point, because this mapping obviously is not Gatu differentiable at 0. And when we say that a Banach space or norm space is Gatu differentiable, we mean that for all x, or all non-zero x usually. But for the function that we examined here, the norm of x to the 2, the situation is different. It is differentiable. So at 0, I mean. So it is better to define smoothness at a point. Here, I can write smooth at x, and I can write here is smooth at x0, and this one at x0. And also we may write this one, because after the region I do this, the norm is Gatu differentiable at x0, and we have for the Gatu derivative this j of x over the norm. Here we know that j, after doing the proof, and j will be single valued in this case. And here phi is the norm of x. It is interesting because here we have just the duality mapping is single valued, and here we obtain the Gatu differentiability, and plus this interesting assertion means that Gatu derivative is linear, and because of this, so many people mention in their definition for books and their papers that Gatu differentiable is the existence of the limit, and be the same to a linear mapping on the space like that I brought there for here. The proof is interesting because we need the ideas. Consider this mapping from 1 to 2 statement. We consider this mapping to showing that this one is continuous. It's enough to show that if xn converges to x with the norm topology, then we need to show that j of xn goes to x in the weak star topology. And we make this one. And the interesting results that we reviewed last session says that we consider this xn in S. And we know that B star is weak star compact. This is Banach al-Oghu theorem. And we know that J of xn for any selection is a subset of B star. So by the compactness, weak star compactness, we conclude J of x converges in cluster, and weak star cluster to some point like Y star. We have xn, j of xn, by the definition equals to this one, and because xn is in this sphere, we have this equals to 1, and this one is by the cluster convergence and the definition of the weak star topology. This one in cluster converges to here X and converges to X, and we have, because it is strong topology and this weak star and cluster, we have this. So here we see that we may write this one like X and J of X. And since by the assumption E is smooth at X0, smooth at this point, we obtain that J of X equals to Y star. Since we have a fixed J of X for any cluster points of this sequence, it follows that it converges to the it means that J of Xn converges in weak star topology to this Y star, which is J of X. So we have here used the assumption 1. I need to put here X0 because by this assumption X is X0 and we have here X0. For 2, this one is obvious because we have for all selection, so we have for some selection this statement. And the only thing we need to do is proving this implication from 3 to 4. And assume that, and from 4 to 1. For showing this one, this is Gauss differentiable. I wrote here an inequality that I cleaned up. By that inequality, I need to write it again. Y and J of X0 over X0, this normal 0 plus Y, because we have Y and J of X0 plus lambda Y, because we are going to tend lambda to the 0 and X0 is not 0. So we can assume that this denominators are non-zero. And by the continuity here of G, because we see that here is weak star continuous. So this one, when lambda goes to 0, tends to J of X0. And this one converges to X0. And so by the sandwich theorem, we obtain 4. And we see that here exactly the statement that is mentioned here at this point. It's enough to show the implication 4 to 1. And This one is obvious also because if we have this statement, then here we have this one, and the limit here, the limit is constant. I mean, we have j of x0 over the norm x0 and y, and is equal to the norm of x plus lambda y minus x0 over lambda, because we have this one by 4 and this one is constant. The limit is constant, it exists. And here we have this element, and for any selection of j, it doesn't matter which one, because here we have this one for all y, and for any selection we have this one. It means that j of x0 over the norm of x0 is singleton. So the proof is complete. Question. The major difference between the two differential equation is that the limit is, this point was, where is it? Yes. The difference between the Gatu and Freshe is that for Gatu we have for all y, but for the Freshe differentiability, we say that the limit is uniform for all y. And there is another notion that about uniform Gatu differentiability. Uniform Gatu says that the limit exists uniformly for all x non-zero. So there are some examples that you may see in the books for LP spaces, LP like this one, and you have seen, if you have worked in this area, that it is Gatu differentiable, it is also Freshe differentiable, and even it is uniformly Gatu differentiable, and even uniformly Freshe differentiable. And I will write the definition and compare the definition and their equivalence forms. And for these mappings, if we consider phi of x like this for any p, for HP, then phi prime of x, the norm of x at this point, and over omega is p by the sine of x omega. And for C0, L1, L infinity, L1, L infinity, right here, they are not smooth. We saw that by this theorem that even R2 is not smooth with the, we consider this one, I write this, with this one is not smooth. If you see the videos of the first session, you may be convinced about this last one. So I review the forms of differentiability that we had. First is that the limit of, for the norm I write when we have this one. We say that the norm of a space is Gaussian differentiable if we have this state. This one exists for all y in E. We say that so it is Gaussian differentiable, or it is the norm is Gaussian differentiable. And if this one exists uniformly for each y in SE, then we say that the norm is pressure differentiable. And if we have this one uniformly for X and SE, we say that the norm is uniformly Gaussian differentiable. Also, we may write this limit uniformly for all X and Y and S. So uniformly for all X and Y and SE, then we say that the norm of E is uniformly pressure differentiable. The last one sometimes is called, when the norm of a space is uniformly pressure differentiable, we say that E is uniformly smooth. We know that the first one equivalent to say that the E is the space is smooth. And we know that for the first one, this mapping from E to E star is norm to weak star continuous. For the second one, we have a result that says this J from E to E star, which is obviously here, the space is smooth and single value then. And J here is norm to norm continuous. For the third one, when the space is uniformly Gaussian differentiable, we have this statement: J is norm to weak star uniformly continues uniformly for the bounded sets, bounded subsets of E. And for the the last one, when we have uniform smoothness or uniform Freshen norm, then J is norm 2. Norm uniformly continuous but uniformly on bounded sets. The first one, they are equivalent. You may check for the others that are they are equivalent or not. The first one is by implication, but 2, 3, and 4 are just an implication. So we need some notions first, then we back to these definitions about differentiability. There are situations that we don't have a differentiable function, but in minimization, we need to have some kind of differentiability, and there is an interesting notion that I mentioned here. It's called subdifferential. Let f be a function from E to R. I write f instead of phi that we had. Define del f of x be this x star and E star. So del f is a function from E to E star, and then we will see the connection of del f and the duality mapping. We see that they are equivalent and the same in many situations. And let this one be convex. We need the convexity for the existence of these elements, and they are, after I write this condition, we call them subgradients. So this is subdifferential, and this one is subgradient. And we have y minus f of x for all y and e. The elements of E star that satisfy this inequality for all y and e are called subgradients. And this set is subdifferential. And the question is that, is it indeed non-empty? And what is it geometrically? First, the subgradients here correspond to the hyperplanes supporting the epigraph indeed. I show you on a graph in R2 what the subgradients are. First, we consider this easy graph and this function y equals f of x, but we don't know that in this point f is differentiable or not. But we may consider here a tangent vector. The tangent vector here depends on another vector, which is a perpendicular vector, and we find the equation for this line here. You know that the gradient can determine this vector by this one, the gradient of f of x minus y, which is, if exists, imagine that if it exists, it would be the gradient of f and minus 1. And for this vector, we may write this like g and minus 1. So is there any question? Board is not clearly seen. Oh, I'm sorry. So we consider this vector and we write the equation for this line, the tangent line here. It is g minus 1. That consider some point here like x tilde and f of x tilde. It's not f of x tilde, indeed, it is y tilde, the point on the line, and we may obtain the equation of the line by this way, that y tilde minus f of x, because this point is on the line, and we need to have this one be 0 to obtain the equation, and this one equivalent to say that j. I write the product because I need to extend to Banach spaces. I like this one, j of x tilde minus x. This is a product in the real line, but we may. And minus 1 multiplied by this one and bringing over there is y tilde minus f of x. By supporting this hyperplane, we mean that this line is in one side of the epigraph of f. This is the epigraph of f. And to be in one side of this, we need to have this inequality that the y of the line should be less than the f of x tilde. So we obtain this inequality and write this inequality to have this line in one side of the epigraph. This is inequality, we need to have that. And if you change the variables here and write this one by x star and change this one to y and change this one. We don't need this one because we have this and this one, and this is y, and exactly we have x star and y minus x less than y minus f of x. So we obtain the definition of the subgradient here. Y minus x star less than y minus f of x. It's instead of x tilde, so we have f of y here. So by this geometric interpretation of the subgradient, we verify some properties of the subdifferential for subgradients here. The elements are called subgradient, and the multi-valued map belief is called subdifferential. We have interesting result concerning this notion. For example, if f of x be the easy example, the absolute value, and you know that for this point, f has no derivative, and f is not differentiable at this point. But we may define subdifferential for this point. Indeed, if we write the round of del f of 0 at 0, we have, because the space is reflexive and the dual is the same, we may write an element like I write x star, and such that we have this inequality y minus 0 x star greater than f of y minus f0 here is 0, and by computing this easy, I can write by multiplication here, and writing this, we have less than, it is inverse 1, less than the absolute value at, it is equivalent to say that x star less than 1. So we deduce that this subdifferential is the set, the line segment, closed line segment minus 1 and 1. So subdifferential is not single value. But the other point is that even if a function is not differentiable, we have still subdifferential. And the other thing is that in which Banach spaces subdifferential is not empty. It's the question. Fortunately, the answer for convex functions in Banach spaces, when f is continuous, is positive. I write a result here. First, I examine it for the easy case, for the case that f of x be the norm of x. So we need this function to relate to the differentiability. And in this case, if x is non-zero, then we obtain this one. Del f of x is exactly the set x the duality mapping on x over the norm of x is exactly the differential of f in x. They are set, they are not point, both of them. So we may write an easy proof for this. From the first inequality I wrote on the board, we have this. We have this one. This one for all y. And since we have this one, and in view of the definition of subdifferential, we have j of, for any element of j, we have this inequality for all y, so j of x over the norm of x is a subset of, is an element of the subdifferential at point x. The inverse for the converse, let x star be an element of the left of x. By definition, we have y minus x, x star less than the norm of y is the function that we have here. And this one for all y. And now we consider a circle by the diameter equals to the norm of x, because the norm of x is non-zero. And we consider y on the sphere with this radius. In this case, for all y and e, with the norm of y equals the norm of x. And in view of the above inequality, we have y minus x, x star, so less than 0. And from this one, we obtain, by rearranging this inequality, we have this one, and this one is less than the norm of x star norm of x. And on the other side, we may write this as the norm of x, x star, y over the norm of x. This one is exactly the norm of y. And by taking this soup on the left side, because we have this for all the points of the sphere, and taking the limb soup here gives that the norm of x, the norm of x star, by the first result that we discussed, this one is less than the norm of x. I remove this one, we don't need this here. And from these inequalities, we see that the norm of x, the norm of x star equals x star of x, and taking y here, another y, be t of x here, and consider this t be a number greater than 1, then we have writing here by this one. we may write, and using also this one. We may write the norm of x, the norm of x star, t minus 1, equals to t minus y. We take here y tx in this inequality, or like this one, and we have t minus 1, the norm of x, because they are equal, and then we deduce that by eliminating these common factors, we obtain this inequality, and so we have from this one and this one, we obtain x star in the jx over the norm of x. I mentioned another point here, that 0, by definition of subdifferential, we know that f in the del f of x, if and only if f has a minimum at x0. So the zeros of subdifferentials are important. The zeros are the points that 0 isn't, this is a 0 of subdifferential, because 0 is in this set. They are important, and finding algorithms converging to that zeros are interesting for people who are working on optimization. And for the lower semi-continuous proper convex function on reflexive spaces, we know that del f is maximal monotone, and we discuss maximal monotone and properties. No. Before I mention another interesting result in the general case, let E be a Banach space and phi be a mapping from. We go back to the Banach spaces. Be proper and convex function, and assume that phi is Gatu differentiable at a point x0, then we have that del f, or the subdifferential of phi at f, is exactly this point here. It is subdifferential, and this one is Gatu differential derivative indeed. So we see the connection of subdifferential and Gatu derivative. I write a proof for this. Then we use the convexity. First, note that phi of x0 plus lambda v minus x0 is, by rearranging these terms, we may write this one. And by the convexity, it is less than 1 minus lambda phi x0 plus lambda phi z, and consider lambda between 0 and 1 here. No, define y be z minus x0 here, and putting it here, we obtain phi of x0 plus lambda y less than phi of x0 plus lambda phi x0 plus y minus phi of x0. By rearranging, it's easy to calculate phi of x0 minus phi of x0 plus y less than. By rearranging, it is easy to compute minus phi of x0 plus lambda y over lambda. And we have an assumption here. We have in this this assumption that phi is Gauss differentiable. So we use it, and it is reverse. So if we tend lambda to 0, we obtain minus y and phi prime x0. Phi prime x0 is the Gauss derivative of phi at x0, which by the assumption exists. And from this one, you see that it is exactly by writing y here. Y is this one, minus y is x0 minus z, and we can write here phi prime x0 for all y. By changing this y by varying on all sets, we reduce that. Phi of x0 minus this one, this one, plus x0 plus y. So it follows that phi prime of x0 is an element of del f del phi at 0. And the other side, so we have proved that the left side is contained f in the right. Yes. No. We have proved that this one is an element of this. So we have this. And no, we need to show that if we have an element of the subdifferential, this element must be equal to this phi prime of x0. So let x0 be an element of this subdifferential. By definition, we know that phi of x0 minus phi of y less than x0 minus y, x star for all y, and by taking y, because for all elements we have that, we write y like this. And putting here, we have phi of x0 plus lambda h minus phi of x0 over lambda greater than by rearranging these terms. We have this one. And now, by tending lambda to 0, we have this convergence H and phi prime of x0 here. So this one and this one on the side can be written like this. H phi prime x0 minus x star less greater than 0 for all h. And this means that because the vector space here using the coefficients or scalars in the Hilbert space and as coefficients of lambda and tending to infinity, we obtain that phi prime x0 is x star, and this is the point that we were going to prove, that x star is indeed phi prime of x0, and the proof is complete. I have some remarks here to mention, just I don't write on the board. First one is that we know that if E is smooth, then E star is strictly convex, and they are equivalent in reflexive Banach spaces. But for the general case, we know that if E star is strictly convex, then E is smooth. And if E star is smooth, then E is strictly convex. And we know that if E is reflexive, because E and E double star are the same, we obtain that E reflexive. Then the above are equivalent. E is smooth if and only if E star is strictly convex, and E star is smooth if and only if E is strictly convex. And we have the same for the uniformly smooth Banach spaces. We know that E star is uniformly smooth if and only if E is uniformly convex. And we know that also E is smooth if and only if we have this one, and I skip some proofs here because of the time. How about the maximal monotone operator? Are they equal to some, for example, a subdifferential function, or what are monotone functions indeed? Monotone mapping or operator, I say operator. They are important in studying evolution equations of monotone type and differential equations generally. Let X and Y be linear spaces and consider A be a subset of X type X, y, and the domain of A is defined. All the elements in X such that A of X is non-empty, and the range of A is defined. The union of the sets AX for all X in the domain of A. And the inverse can be defined Y and X such that X and Y is an element of A. We consider first the case that Y is the dual space. For example, X star here. We consider this first and then go to the case that we have X times X, but in that case, monotone operators are called accretive, and they are interesting for some reason that I will mention it. Let A be a subset of X star. It is monotone. We say that it is monotone if we have this one, x1 minus x2 and y1 minus y2 greater than 0 for all x elements x1, y1, and x2, y2 in A. It is a generalization of the monotone functions in R2 or mappings from R to R. And we have another notion which is important. A mapping or a monotone mapping it's monotone. It is said to be maximal monotone. Maximal monotone if and only if, I just mentioned it, it is not properly contained in any other monotone subset in the form that we know for the set. It is not contained in any other monotone subset of X times X star. But they have some interesting characterizations that we mainly use that characterization instead of this definition. First example is the J duality mapping from X to X star. You know that this is an example of a subset of X times X star, and it is monotone. J always is monotone. I write the reason here. Because if we write J of x1 minus J of x2, then I simplify this inner, we have x1 2 plus x2 2 by the property of the duality mapping, and minus x1 J x2 minus x2 J of x1, and by the inequalities like Cauchy-Schwarz we have, because it has a minus, we have this one greater than the minus x1, x2, and the same for the other term. And so we deduce that this one greater than the normal x1 minus x2 to the power of 2. And it shows that J is monotone. And it is indeed maximal monotone under the assumption that X is reflexive. So I skip some parts of this. You know the importance of the maximal monotone operators. There is an interesting result due to Minty and Browder that I mentioned here. It is important because it's a connection between the existing results for nonlinear equations and convex analysis. Let's consider EB reflexive and also smooth. And let A be a subset of E times E, and let this one be monotone. Then we have this equivalence, power of A plus lambda J, the duality mapping, equals to E star if and only if A is maximal monotone. You see that here we have a lambda. We can say that for all lambda or some lambda, they are equivalent in the proof. We will see this proof. Let consider this implication and assume that for some lambda we have this equality. So we want to show that A is maximal monotone. So assume by contradiction that there exists some x0, y0 in E times E star. This is by contradiction. And we want to reach a contradiction indeed by this assumption that x0, y0 not being the set A, which is monotone. And we assume also that because we have assumed that A is not maximal monotone, so there exists some x0, y0 in which is not in A, but we have this inequality for all x and y in A. This means that A union x0, y0 is another operator which contains A, and this contradicts the maximal monotonicity if we show that x0 and y0 are elements if we show that they are in A, this is a contradiction indeed. But our assumption is this one, and we want to get this, and we assume that this one is not correct first, and we consider some x0 and y0 and continue to see from this equation, we may, because it's whole of x star, so we can find some. It's the range of A and lambda j. So there exists, and it's whole of x star. So we may find x1 and y1 in A with this property that y1 plus lambda j x1 equals E star, and we have that y0 lambda j of x0 is an element in E star. So it is possible to find such point, such element here. By the assumption we have here, I call this one star, and this one I call this one double star. And by star, we have 0 less than x1 minus x0 and y1 minus y0, and it is lambda x1 minus x0 j x0 minus by this equality j of x1, and by the monotonicity of j, we have this one less than 0. So we reduce that this term is 0. For possible questions, there is no question. Since this one is 0, we obtain this one is 0. Considering this, we can write x1 to the 2 plus x0 to the 2 equals to x1 and j of x0 plus x0 and j of x1. And this one obviously is less than the 2, the norm of x0, norm of x1. From this easy inequalities, they are positive, and so we may write x1 to the 2, x0 to the power of 2 equals to x1 j x0 plus x0 j 1, and I sometimes write j and this one equals to x1 and j of x1 from this one and this, we deduce that j of x1 equals j of x0 by the smoothness, and from 2 star from this equation, we also deduce that y1 equals y2 and y0 was y1, and this one we know is in ax1, and from this one we also deduce that since J inverse is single value, then we deduce that x1 equals x0, and by this we deduce that is ax0. y0 is an element of ax0. This is a contradiction, so we have proved the result. I keep the other side. The subdifferential of lower semi-continuous convex function, as you see, is important, and it has some relation to maximal monotone operator, as you see, and I mentioned another interesting result in this regard. Let phi here mapping, we can consider our bar, which means that it can take infinity, but it is proper. We assume that phi is proper, lower semi-continuous, proper, and another assumption that it is convex. Under these assumptions, this theorem says that the subdifferential of phi is maximal monotone, which is interesting proof. For the general case, the proof is complicated and needs more time, so I consider a proof that is short, and it's for the spaces that are reflexive and smooth. So we assume that it is reflexive and smooth for the general case. I may read the works of Rockefeller, and by these assumptions, first we note that maximal monotone means that by the previous result, it's enough to show that J of x plus round of phi of x is the entire x star. We need to show this one. Show this equation. Let some point in E star, and we show that there exists some point here in this set, and this set, their addition is the element y. We define f from E to R by this term 1 to the normal x to the power of 2 phi of x minus x and y. We define this. It is lower semi-continuous because the norm 2 is convex, and lower semi-continuous phi, by the assumption lower semi-continuous, then is easy to, it's linear, and so it's lower semi-continuous. So I write it is lower semi-continuous. And it is convex also. You know that norm 2 is convex, phi is convex, and this one is linear. And we have also this one, f of x is infinity when x goes to infinity. It is not obvious. We need to show this one indeed. First, to show this one, we need to show that there exists x0 in E star and P in R such that phi of x greater than x and x star plus P. If we show this one, then we may write, if we have this one, f of x is plus phi of x minus x star, and this one would be greater than b plus x and x star minus y, and this one would be greater than minus under this assumption. Norm of x minus x star minus y. It is easy to show this one. And we see that the power here is 2. This one has power 1. So this one, the sum of this one goes to infinity. And since this one greater than b, so we see this term goes to infinity when norm of x tends to infinity. But for this, there is an easy proof. It is an application of Banach theorem. Consider A be the epigraph of phi, which is a subset of E times R, and it is closed and convex, and consider some point like x and r not in A, and we use the Banach theorem to separate them by linear functional from the dual like this one in the E star times R, and it separates A and B, and using this separation, it is easy to have this one. This is exactly x star and times lambda to the fixed x and r, we obtain B. So so far we have that f of x has the property that its norm, its limit goes to infinity as the norm of x tends to infinity. By known result for convex mappings, for lower continuous mappings that goes to infinity, we have some x in E, which is the minimum of this infimum. The infimum is achieved at this point, at least, and this yields this one, x0 to the 2 plus. This is the definition of the minimum. x0, y less than 1 over 2 plus y of x minus x and y for all x, and from this one, by rearranging phi of x0 minus phi of x less than x0 minus xy plus 1 over 2 norm of x minus x0 to the 2, and this one, easy to see that less than x minus x0, j of x the first inequality that I mentioned. And from this one, phi of x0 by simplifying x0 minus x, y minus j of x. For all x, we have this one. And now we may take x be px01 minus t, u for any u in t. And assume t is between 0 and 1, and by simplifying here, we obtain by writing x instead of the original one, t phi x0 plus 1 minus t phi of u. And we know that this one exactly is 1 minus t phi of x0 minus phi of u. And this one, by the above inequality, we have taken x like this, and this is less than phi of x0 minus phi of x. And this one less than 1 minus t x0 minus 1 minus t u, y minus j t x0 plus 1 minus t u. And by eliminating the common factors, we have this inequality for u. Why we have done these calculations? We want to tend j of x0 when t from the left tends to 1. Is the usage of the norm to which star continuity of the duality mapping. And from this one, we obtain phi of x0 minus phi of u less than x0 minus u and y minus j of x0. We had this one, but we couldn't use directly, and we wanted to have this one. Here we have this one for all x in E, and we obtain this one. Here x is variable, and by this method, we obtained j here by a fixed x0 by changing the variables. And so we use this one to have y minus j of x0 in the del phi of x0. And this is the result that we wanted to show j of x0 plus the norm del phi of x0. And the proof is complete here. Not displayed. So we have a topic here about equity accretive operators. Accretive operators are interesting because we have here, instead of monotone case, a subset of E times. I consider here E. It is called accretive if we have this inequality. Because this is not EX star, we want to use a sort of inner product and or the elements of E star. So we have added some J. This is the duality mapping, and we use this one as elements in J of. If we have this one for all J of x1 minus x2 in this duality, and for all x1 and y1 in A, then we say that E is accretive. And we may define, as before, maximal accretivity or M-accretivity. We show that this definition, which is M-accretive, will be maximal monotone. Has a maximal form. It is indeed maximal accretive because for the accretive, we have mappings from E to E, the set valued mappings. So we define this, that A, assume that A is accretive, then we say that plus R of I plus A equals the entire A. Then we say that M A is M accretive. This is the definition that we have, and it is easy to show that this one is equivalent to say that this equality holds for all lambda greater than 0, and we have similar results for this new definition. But there is something that is very interesting about accretive operators, which is a geometric property. We can show that A is accretive if and only if we have x1 minus x2 less than x1 minus x2 plus lambda y1 minus y2. And this for all x1 and x2 in A should be whole, and for all lambda greater than 0. And why they are equivalent? It's a corollary of a result by Catu that says this lemma, an easy lemma, says that there exists some element in J of x such that y and J of x greater than 0 if and only if we have this inequality. X plus lambda y for all positive lambda. And you see that from this lemma, directly we obtain the above equivalence, because the definition of accretivity is like this by y1 minus y2, y2 j of x1 minus y x2 that we had here. So I just write an easy proof for this inequality to justify this. We know that norm 2, this lemma, norm 2 is indeed x and j of x. We prove this implication because this term is positive. By the assumption, we may write this, and this addition is this term, and by Cauchy-Schwarz inequality, like we have this one, which is the result by simplifying power by this norm. And the converse is also easy. I skip this. And another notion that is important in this area is resolvent which is defined by j lambda x. It's different from duality mapping. It's resolvent of A, which is defined by this one. For any x in the range of I plus lambda I. It is well defined when A is accretive. And I prove the well-definedness of this. And another notion is Yoshida approximation of A, which is defined by this. It is important sometimes for solving differential inclusions. We use this one to obtain a optimal single-valued mapping to solve a differential equation instead of differential inclusion. And we show that this one for M-accretive mappings goes to A0 x, and I show this one. So for it's better to show the definition of J lambda to be well-defined indeed. We may write, because we have taken the elements here, and a typical element is like lambda y1, or considering x2 plus lambda 2 in our I plus lambda a. If we have this one, then by the property that mentioned here, we may write x1 minus x2 less than the norm of x1 minus x2 plus lambda y1 minus y2. And since we have this equality from this one, we have 0, and so x1 equals x2, so it is well defined also. It is also non-expensive. It is easy to show. I skip this one. And another property which is interesting, if we have an accretive mapping, then it is maximal accretive. It is an easy exercise you may check. I skip this one also because of the time. And what is A0 of x I mentioned here is all the elements in A of x such that the norm of y is equal to the distance of 0 and A of x. In the case that the space is uniformly smooth, for example, then it will be reflexive, and we obtain representation for M-accretive mappings, and then it will be closed and convex. And since it is closed and convex in A of x, closed and convex in a reflexive Banach space, so it is non-empty. If in addition x is strictly convex, then this set is single valued. There is an interesting result here. If A M accretive, then A is closed. Let xn converges to x and yn converges to y in the strong topology. And assume that xn and yn are in A. We want to show that A is closed. We need to show that it's graph closed, and we consider here a sequence in A by these assumptions. No, we need to show that x and y is an element of E. We see by the accretivity that the norm of xn minus u less than xn plus yn u plus lambda v for all u and v in A. We have this one because xn and yn is in E, and we have also this one. Then taking limit here, we deduce that the norm of x minus u less than the norm of x plus lambda y minus u plus lambda v for all u and v. And since A is accretive, this implies the existence of some point in A with this property, because in this case, I plus lambda A is the entire A. So we may write this one. X plus, we have found this U and V such that equals to this one as a typical element of E. By substituting in this inequality, this U and V instead of the previous one, we see that X is U. The inequality is here. If we put here this equality, we have 0 here. And so they are equal. And so by this equation, we have y equals v. This one is in AU and u equals x. So we may write A of x. So we have proved that A is closed. I write everything here inside the board. Another result here is about demi-closeness. If we have X is uniformly, or in a better case that has pressure differentiable norm, and A is mx iterative, then we deduce that A is demi-closed. It's interesting and very useful. Demi-closeness means that if we have xn converging to x in the norm and yn converge to y in the weak topology, we need to show that x and y is an element of A. Here, the topology is the weak topology. But we need to show this. And here, we have chosen xn and yn in A. To prove, we just note that by the definition of the creativity yn minus v, j of xn minus u greater than 0 for all u and v in A. We have this one. And we know apply the assumption of pressure differentiability and the fact that the duality mapping under this condition is norm to norm continuous. So this one converges to j of x minus v. So we deduce the following: y minus v by converging n to infinity, j of x minus u greater than 0 for all u and v in A. And from this, the fact that A is equative shows that we have this equality, and so we may choose U and V in A such that we have this equality because it's a typical element of E, and so we deduce from this one and this one that putting here in that inequality x minus U to the power of 2 less than 0, and so x equals U. This means that V equals Y by this equation. And so X and Y is an element in A. So today will be finished in 3 minutes. I just mentioned another result. That if the theorem that says A is uniformly smooth and uniformly convex, then for assume that A is M accretive, then we have A lambda x converted to A0x. It's the minimal section of x that defined before when lambda goes to 0, and Yoshida approximation here converges to the minimal section here is interesting. And also we have that the domain of A is convex, and it is very important for solving some differential inclusions. And to prove the first one, I just say the outlines that we have this easy statements that for Yoshida approximation always hold. For example, the first one, I just write this one. Yoshida approximation on X can be written by this definition like this, and we may write like this one, I plus lambda A, J lambda X, because X is an element of this one. J lambda is the inverse of this operator minus J lambda X over lambda, which is A J lambda X by simplifying. And the other one is the same. And I just let here lambda goes to 0 and assume that A lambda n X weakly converges to Y. We can assume this one because A lambda n is bounded by this one. And the space is uniformly convex, so it is reflexive. So we may obtain a subsequence converging weakly to some point without loss of generality. We write lambda n
And the minimal section here is unique because the space is strictly convex. It's mentioned that the minimal section is single point. So if we show the convergence, the strong convergence, everything will be proved. And for this one, we need to show that if we show that the norm of A lambda nx goes to the norm of yn by the Caddy-Clay property, because we have the weak convergence, the norm of this one goes to the norm of this one, and the space is uniformly convex by the Caddy-Clay property, the convergence, the strong convergence will be concluded. So just we need to show the norm convergence here. I think this session will be finished in a minute. We note that we use here also the demi-closeness. Since A is demi-closed by the previous one, and also since we have J lambda x, by definition is lambda n, A lambda nx, and it's bounded, and lambda m goes to 0, this one goes to 0, and A lambda n x, this one belongs to A, J lambda n x, and this one goes to y weakly, and by this, it follows by the demi-closeness of A implies that we have x and y in A. Also, by the lower semi-continuity of the weak convergence, we have the norm of y less than the limit of A lambda n x, and this one, by definition, is less than A0 x. So we obtain this one, and this one rate is greater than A0 of x. Why? Because y is an element of the range of A. We showed here by the demi-closeness. And therefore, we have A lambda n x goes to A0 x, which is the norm of x. And then by the Caddy-Clay property, I write it as kk, which have A lambda nx goes to y, which is A0 x. Thank you. That's all. Is there any question? Why is strong preferred to weak convergence in application? Yes. Yes. The question is that why the strong convergence is preferred to solve the differential inclusions. Indeed, we need to have strong, it is preferred here. And because of that, so it is, I think, trivial. Thank you.